Hi everyone, I'm Trina. I have a demonstration that I want to show you as we start into chapter 17. So chapter 17, we're covering superposition of waves. So essentially we're going to talk about having more than one wave in the same medium at the same time. So right here, this would represent kind of a snapshot graph. These top beads are representing a wave that has a specific wavelength, which would in turn would be a specific frequency, a certain speed because it would be a specific type of wave. Notice these blue straws, essentially is what it is, represents where the peak is, and then we have a shorter blue straw that represents where the trough is for our wave. Now I have two additional waves that I can slide in, and we would essentially represent having these two waves in the same medium at the same time. So the second wave has half the wavelength. So the original wave that you're seeing right now has a specific wavelength. This one that I will slide in will have half of that wavelength. It has a smaller amplitude as well. So I have to slide this into the contraption. Oops, sorry. So this would represent the top beads, still would represent what the medium overall would look like at this moment in time. So this would still represent the snapshot graph. The bottom beads, those green ones, are representing what this new wave, this second wave, looks like. But ultimately, what determines the median, these top beads, is the summation, the addition of the displacement of the original beads plus the displacement of this new wave. So the resulting medium does not look like a sine wave anymore. And that's because in some places we get the addition of the peak of the new wave to something in between the peak and trough of the original wave. But ultimately, by superposition, we mean whatever displacement this new wave is doing or creating in the medium, plus the displacement of the original wave, those displacements simply add together to give us the overall displacement of the original wave. I can slide this new wave. Let me slide it and line a peak of the new wave up with a peak of the original wave. We get an interesting pattern this way. So the peak of the new wave lining up with the peak of the original wave, we get these nice high amplitudes because those positive amplitudes are adding up. But because the wavelength of this new wave is half the original wave, we're also getting a peak of the new wave adding to the trough of the original wave. And so we're getting near almost zero right here. It's not perfectly zero because they don't have the same amplitude, but the negative displacement of the original wave plus the positive displacement of the new wave is causing a cancellation to give us almost no displacement at all. So superposition simply means adding the displacements of the waves that are all existing in the medium at the same time. Now, something interesting occurs when we have two waves. Oops, sorry, hitting my bookcase. So the second wave I have that I'm going to slide in just a second is actually identical to the original one. It has the same wavelength, it has the same amplitude. And so I'm going to slide this in and we're going to see superposition again, meaning the displacement of the two waves just add together. But when we have two waves that are identical, if the peak of the two waves, if they line up perfectly, this only can happen with two identical waves. So if the peak of one lines up with the peak of the other, then we get twice the amplitude here. We have a maximum displacement at the very top. It's the same as it was before. So these two waves we would call and say they are perfectly in phase with each other. They have peaks at the same time, they have the troughs at the same time, and same location. And so perfectly in phase means that if the peaks line up, we get this double the amplitude wave. So it's still superposition, meaning we're adding the displacement of the individual waves. But this will be called also constructive interference. If this represented a light wave, we would see a brighter light if these two waves are interfering constructively. If this was representing a sound wave, so just the pressure variations in the air, this would represent a louder sound. And this perfect constructive interference occurs because these two waves are perfectly identical. Another situation would be if one wave, if the peak lined up with the trough of the other wave. So in this region right here, the original wave, notice its peak would be where that straw is, but because it's lined up with the trough of this new wave, the positive displacement added to the negative displacement essentially gives us zero. So this medium will essentially look like nothing was happening. But that's because of how those displacements are adding together. We would call this a situation of perfect destructive interference. It's kind of silly, but I like to think of it as they destroy each other. And then we don't see a wave. Now, that's not really what's happening. It's just that the positive displacement of one wave plus the negative displacement of the other wave, when we add them together, they add up to be zero. So this situation is called perfect destructive interference. Now, these waves can certainly meet up somewhere in between. They don't have to line up perfectly in phase or perfectly out of phase. The out of phase is when the last situation we had. We could have something in between where they don't line up perfectly. We still get, in general, this same wave pattern. The amplitude's not exactly double, which is what we see with perfect constructive interference, but it is larger than it was for either one individually, and the overall wavelength is still the same. We would still consider this constructive interference, just not perfect constructive interference. So perfect constructive interference is this situation where the waves are perfectly in phase, the peaks line up, the troughs line up, so we get twice the amplitude here because the waves are identical. We have the overall medium, we still see the same wavelength, just a much larger amplitude. So one thing we're going to look at too, if we think about wanting to shift from perfect constructive interference to perfect destructive. So I want to move this bottom black wave, this new one, in such a way that we will get destructive interference. I would need to line the peak of the original up with a trough of the second one. That is a half of a wavelength. Between a peak and a trough is half a wavelength. I could shift this. So right now we're in perfect constructive interference. I can totally shift that bottom wave and still have another situation of constructive interference. I could, instead of having this peak line up with this peak, I could line this peak up. Sorry, it's hard to find my videos backwards from what I'm doing, so I'm struggling a little bit, sorry. I can line this peak up with another peak. If I slide that over, in the area where both waves still exist, it's still constructive interference. So I took this peak that used to be all the way over there, lined up with the other original peak, and I moved it so that it lines up under this peak. I moved it a distance of one whole wavelength because I moved it from one peak to the adjacent peak. I can move it another wavelength and still see that perfect constructive interference in the region that both waves exist. So we have a smaller region in which both waves exist, but where they both are in phase there, it is still perfect constructive interference. So what we find is a shift of one wavelength. We still get constructive interference where both waves are still there. Shifting it 2 wavelengths from the original allows us to see constructive interference as well. If I want to go from constructive to destructive, I shift from a peak to a trough. And so I have shifted half a wavelength. This is something to keep in mind. I'll talk about it more in an additional video, but keep that in mind. I find this visual can be helpful in helping us talk about the interference some more. So this chapter, superposition of waves, simply means the displacement of the individual waves is added together to give the overall displacement of the medium. And then we're going to talk perfect constructive interference and perfect destructive interference. With those, we're going to talk about some applications. So something we might hear or see because of this interference. Something you might be familiar with already would be noise canceling earphones. So really nice noise canceling earphones will analyze the sound coming in and create an opposite sound coming out. And so you're going to get peaks lining up with the troughs and they will cancel each other out. Kind of cool. So I'll continue in another video.